Oh, you guys sit over there. You want to play cameraman today? Sure. Thanks, bud. Good morning. Good morning. Good morning. Happy Monday, everyone. Grown. One more week until spring break. Who's more excited, the teaching team or the students? There's an interesting question. Don't you have to do work over spring break? No. See, okay. I'm union. I'm Tony Farrar from the Mechanical Engineering Department, and today I'm here to tell you about fractals in Python. But first, a reminder of a couple of updates that we've made lately. Oh man, my clicker. Make sure I get this going. Bop. Aha! We have updated the course schedule. What do you need to know? Well, you need to know that JavaScript and Python are now in the rearview mirror, and the thing that we are working on is the core skills demo, which is either posted or will be posted this afternoon. So keep your eyes open. We're ready to roll. It'll be due Monday after spring break, although it's designed to be done this week. We will have support for you, details to come on Wednesday on what it'll look like over break. And then we'll get into doing the good stuff. So this week, you should be done with JavaScript and Python. This is probably starting to look a little familiar. In addition, we want you to work the core skills demo, and by the end of the week with your group, pick the platform that you're going to make your semester project in. Today we're going to talk about some more coding tricks in Python, and then on Wednesday, special presentation for you on ways that this is going to be useful moving forward in your engineering career, and some more Python help. And then lastly, on Friday, we'll have a code sprint that's going to be a debugging challenge. We're going to give you a code that doesn't work and invite you to fix it. So get hyped. Just a reminder, we've got 3 platforms. Those 3 platforms that you can choose from are Android, iOS, and web. Each one comes with some pros and minuses that make them about equivalent in terms of difficulty of getting the project done. Pick the one that best serves your need. Any questions? Announcement. Apparently, we forgot some zeros in the grading app that we write. And so there's a couple places where I think some hundreds got turned to tens. If that happened to you, we're working on it. And I think everybody that did the code sprint on Friday got a 5 out of 100. Let that be a lesson to you. No. Typos. We'll get there. This is what we would call a logic error, right? The code ran, it just didn't do what we wanted it to. So we're working on it. We'll get there soon. Questions? How are we doing? All right. Promise, today's going to be really visual, so hopefully you enjoy that. We're going to play a game called Marching Orders, and the way it works is that you're going to start by picking a location inside this little circle. XY grid here, 0, 0 at the center. We're going to do a little bit of fancy math that's going to decide how to move to a new location. And then we're going to repeat that math a predetermined number of times, let's say 100. So we can put that in a little bit of a conceptual loop here where we're just going to keep doing new math, or the same math to new points over and over again. And then we'll ask a question. At the end of however many steps we took, are we still in the circle? If so, we're going to color our starting location where we originally came from blue. If, on the other hand, we are outside of the circle at this point, we'll go back to the starting location and color it yellow. Sounds simple enough. All right, let's do a couple examples here. So we're going to pick a starting location, say right there. And I'm going to do some math that's going to decide where it should move from there. So we're going to take the values of x and y there, do a little bit of math to them, and it gives us a new x and y, which is right up there. And so we move over there, and then we repeat this 100 times, and we end up with some sort of a wandering path. And in this case, that point stayed, that path stayed inside our circle, and so we'll go back and color the original spot blue, where on the other hand, we could try a different starting location like this one. And from there, if we do our fancy math a bunch of times, we end up wandering outside of the circle. And strangely enough, with the type of math we're going to do, those are the only two options. There's no option that steps out of the circle and comes back. And so in this case, we're not in the circle anymore, and so we'll go back and color our original starting location yellow. If we did that to every point in the circle, we would end up with a picture that looks like this. And as you can see, there's not much interesting out in this region or out in this region, so we're actually just going to look at this rectangular box that goes from -2 to 1 and -1 to 1, like so. So, what did we just do? We did an interesting thing, and I'm going to tell you all the details on how it works, but we're going to start high level and kind of dig our way into this mess. Yeah. I did make a fractal, so if you know what this is already, cool. If you don't, fractals are a neat type of math trick where you do relatively simple math and very complicated behaviors start to emerge. And you're about to see that happen here. But what we did was, we started with some x and y, and we fed them into some algorithm. In this case, that algorithm does some math to x and y, and when it's done, it spits out a new x and a new y. Ba-ba! And so we moved to a new point. I got really excited about the slide animations this weekend. But we didn't stop there. We took that output and used it as the input to the algorithm and ran it again. And again, and again, and again, and again. And that's a process that we call recursion. We take the output of something, feed it back in, and interesting things start to happen. In this case, really complicated behavior emerges. So just to prove that I actually wrote this code one time, here it is running point by point and deciding whether or not we're still in the circle or not, and it's coloring these points appropriately. And we're going to write the code that does this over the next couple of class periods. Turns out it gets more interesting if you use a finer grid. There it is in black and white instead. So this is the Mandelbrot fractal. Who's seen this before? All right. Cool. Who's already written the code to do it before? 2. All right. I'm really curious to compare how we do it. So, I guess the big question in everybody's mind right now is, what is the algorithm that I used to determine the new position? And it turns out, this is the great part about fractals, is that it's very simple math compared to the things we could do anyhow. So we're going to start with some initial point, x0, y0. And then we're going to calculate a new x that looks like this and a new y that looks like that. So you're going to take x0 and plug it in there. You take y0 and plug it in there. The first time through, we haven't done anything for x and y old, so we can just let those be 0. So everybody at once, if these are 0 and this holds some number, what's that going to be equal to? if these are 0 and this has a number in it, what value ends up there? The number. Ditto here, right? This is going to be zeros. Take that number and stick it there. But now comes the weird part. That new value now becomes our old value. And this new value becomes this old value. So now we have a number, and the original number, and we do the math again, and it gives us a new number. And we just keep looping through that. Don't worry, I'm going to give you a chance to practice it in just a second. Every time we do that, we want to find out if we're still in the circle, so we calculate the radius of our point, right? So you can imagine that we could draw a line from 0 to our point, and the radius of that line would be x squared plus y squared square root. A little bit of Pythagorean theorem here for you. And so let's do a point. How about right here, point 1, point 3, grab a piece of paper. And we're going to take 1 minute on our own to start this one. Okay, so everybody get something to write with. And the question that I want to ask you is, which of these 3 statements is true after 4 iterations? So remember, the first time through, what's x old equal to? So, the first time through, what's x old equal to? 0. How about y old? 0. So then we stub our numbers in, which look like 0.1 and 0.3. And we're going to run this loop now 4 times. Let me give you a minute to work it on your own. Let's see where we end up. Well, 1 minute and 5 seconds, as it turns out. Yeah. What is r? It's the radius, so sum of the squares and square root, like the size of a triangle. Probably should have showed r up there, huh?
The radius of the circle dependent on the initial point, or is it based around
The new point, or new, I guess it should be.
Okay.
Yep, the new radius. Need another minute? Yeah. All right, 1 more minute. What's that? Oh yeah, it's like the best of thermo and the best of fluids put together. Nah, it turns out. All right, let's take a quick poll. How many people say that the newest radius after 4 iterations is smaller than 0.28? Couple hands. All right, how many people say it's equal to 0.28? All right, how many say it's larger than 0.28? How many are completely not sure? All right. Let me work this one for you. We'll give you a chance to do a second one. Here's the full table. So the first time through, x is equal to 0.1, y is equal to 0.3. We sub those numbers in here. These are 0 and these are 0, so x new and y new become 0.1 and 0.3. We calculate the radius by squaring both of them, adding them together, taking the square root. How many got at least one step in, maybe? Did you get a step in? Okay, so maybe just not enough time here. So, once we take those values and stick them in for x old and y old, now you have 0.1 squared plus minus 0.3 squared plus 0.1 squared. And you run all of that out, and it's equal to 0.02. Here we have 2 times 0.1 times 0.3 plus 0.3. You run that out, and it gets you 0.36. Those things can be sum of squares and square rooted to give us a new radius of 0.36. How many got the 0.02 and the 0.36? How about that? See where we're at there. Okay, cool. A lot more hands there. So next we're going to take those numbers, sub those in for x and y old. X, y, 0 stay at these values. And we run it, and it gives us these points. And we take those points and we run it, and we take those points and we run it. And so r after 4 iterations was 0.3, which is bigger than 0.28. So if you had that, that was the answer there. And an interesting thing happens. As we continue to iterate, as we continue to run this thing is spiraling in, and it's never actually going to run off. And so eventually it gets kind of boring because the number just kind of stays the same. And so the path spiraled in. Let's write the pseudocode for this really quick, and then we're going to run it a second time. Give you one more chance to try the math here, okay? All right, so there's our equations. The first thing that we have to decide is how big of a circle we want. Now, we said something that went from like -1 to 2, something like that. So let's make a circle of radius 2. Now, if I want to apply this algorithm at every single point, what do I need to do that? Yeah. Just come up with a loop that applies to every point. Are you a plant? All right, now, at each point, we want to run that algorithm. Yeah. I'm sorry? How big is a point? It's however big we decide it is. That's part of the fun. We get to define this grid based on the number of points we're going to run. At every one of these pixels, we need to set x old and y old to 0 and our iteration count to 0. All right, that's where we just started, basically. Now what do? We want to apply this to a single point. What's going to show up? Well, somebody describe to me what we just did with this. How about that? What happened first? Yeah, I'm trying to figure out if we're going to run this algorithm now at every single point. We've got the loop that gets it going at every point. Now we just have to run the actual algorithm. So what's that going to look like? We need x and y 0. Yep. Oops, gave it away. I think that was the second thing I wrote. Yep. And what we're going to do then is loop through this thing, right? We said do it 4 times just now, or 100 times, or however many times. And for each one of these loop iterations, we're going to calculate the new x and new y, update those old values, is what you were saying, start them at 0 and then update them. And then update that iteration count. What kind of a loop might that be? A for loop or a while loop? Who wants to use a for loop? Couple hands. Okay, 3, 4 hands. Cool. How many want to use a while loop? A few more hands. All right, give me an argument for the for. Yeah. Okay, so for loop's useful because we can decide how many times we go through it. Why would a while loop be useful? Yeah. We don't know how many times it needs to go through it. Huh. Okay. Once we're done with these, we want to check if that final point is inside the circle, right? And then we're done. As long as we run that for every point, we can paint this picture. And I took this one layer deeper, which will get you what you wanted, I think. For each pixel, we want to find an initial position, x and y 0. Let these equal 0. The iteration count equals 0. Now we're going to loop through the n iterations. The way that I wrote this, is that a for loop or a while loop? If I'm saying do it n times. That's a for loop. Okay. All right, we got some equations to run here, right? We want to calculate x new and y new. That's using the equations here. And then we want to update the old values. That's kind of a weird thing that you can do inside this loop. We're going to take x old and set it equal to x new. So now the next time through the loop, those values get plugged in here. And we just keep looping through. And of course, every time we do this, we want to add 1 to our iteration count. How do I check if we're still inside the circle? Say what? Take the square root of the sum of the squares, like so, right? One thing we could do is skip doing a square root by just checking everything if it's squared, right? Radius squared less than x new and y new. It saves us one math step. If we're going to be looping a bunch of times and we can skip a math step, that's usually advantageous. And so if it is, we're in the circle, and if it's not, we are no longer in the circle. Question here. They're always the original coordinate of that particular pixel. Yep. Okay. So I guess one thing that's missing from my pseudocode here is that every pixel needs to be assigned a value of x and y, which we would use as that x and y 0. How do we get it to map? We're going to play that game in just a minute. Well, probably more like 5, but we'll get there. Okay, like I said, we're going to look at this several times. We'll get there. So I want to try another point. Now, you know what the answer is going to be, right? If it's out here, is it going to stay in the circle or not? Hands up if it's staying in the circle. Hands up if it's leaving the circle. Okay, we're getting there. Let's try running it anyhow. So I'm going to give you 4 iterations again. This time we're starting with an x0, y0 value of 0.1 and 0.7. And we're going to run 4 iterations and see where we end up. 2 minutes. Take it away. Anybody else feel like it's a really good thing that we normally ask computers to do this kind of math? It's a hassle by hand, huh? Picked a very brave seat. Huh? Yeah. So, how many people came up with the idea that it might be a pain to do this by hand? All right, at least we got that lesson down. Who made a spreadsheet? Cool. All right, some people figuring out some hacks around this. How many people say that after 4 iterations the radius is less than 1? Couple hands up, okay. How many people say it's equal to 1? How many say it's greater than 1? All right. After 4 iterations, we're still less than 1. But eventually it is going to be bigger than 1. So let me show you the numbers here. These are going to be posted. I recommend maybe going home and tinkering with this. If you haven't quite got it, that's okay. But it might be more interesting to you as I continue working this code for you to understand the base math that we're doing. So here's how this works. Once again, we started with x and y equal to 0.1 and 0.7. We're going to stick those numbers in as x0 and y0. These are all zeros, and so the next time through, we get the same thing back, 0.1 and 0.7. But now, we had a 0.1 in here, a 0.7 in here, and a 0.1 in here. So that's 0.1 squared, which is 0.1 squared is, thank you, 0.01, minus 0.7 squared. What's 0.7 squared? I'm sorry? 0.049, 0.7 times 0.7 is 0.049, and then the x0 here was 0.1 again. We add those all together, and it gives us this 0.38. And so we keep going, and after 4 iterations, depending on how you like to count, we're either here or here. So maybe it was a split decision on whether we're bigger than 1 or not. And as we keep running, here's the thing that's interesting. You notice that my path now is spiraling out, and eventually right here, up, we are now way outside a radius of 2. This is a 4. Sorry, the font's a little small in the back. The result of which is that we're never coming back. In fact, if I were to drop that 2 circle on here, it looks like this. And here's the part that's interesting. It was the 8th iteration where we first jumped out of our radius of 2. And so as this thing spiraled out, we could have actually saved ourselves some trouble. I said do a for loop. We're going to run it 100 times. If it steps out on its 8th time, what information is being added by running that loop 92 more times? Nothing. There's no use for it. So that's 92 loop iterations that we just wasted on ourselves. So if I wanted to fix that, what would be a great way to make this cheaper? Yeah. Make a while loop that breaks it if we ever happen to step outside of this circle. And here's the interesting thing. We could count every single point that we run this for. We could count how many steps it takes to get outside of the circle. Let's call that Z. So now, instead of just saying, is it in or out, which gave us a black and white image, I'm going to ask the question of how many steps did it take to get out? This point happened to be 8. Another point might happen to be 200. At some point, it steps out. And now we have more information, right? Not just are we in the circle or out of the circle, but how long did it take to diverge? And this is where it gets fun. We can now color these pixels. Okay? So every point, instead of just being in or out of the circle, has a z value. We take x and y, we run it through the Mandelbrot algorithm. It gives us this value of z, and so perhaps this point has a z value of 4. Some other point was 8. Some other point might be 32. And if we keep track of that z value for every point, we could do something like color the picture. So here's my question. What type of data structure might be helpful for storing z? Yeah. An array. Right? We got a table of values, one for every pixel in our image, and here is what you get if you do that. And the fun of a fractal, if math can be fun, is that these things are infinitely complex and never repeating, although you start to see themes. So for example, if we zoom in on this region right here and rerun this algorithm for however many pixels are on our screen, you get this. And in fact, you can continue zooming farther and farther into your image until you hit the machine precision of your computer, at which point you can't represent a smaller number. And so that's as far as we get to go. I wish. No, this is a recording of zooming in, because every time you zoom in, you have to recalculate for the pixels that are in that image. And as we're about to find out, that takes some time. Huh? Oh, I did? Have I looped? Okay. So we're going to write the code that does this over the next few lectures. So here's the pseudocode for calculating that z value. Although, as you remember, I had it looped through n iterations, and we're going to get rid of that by, first off, keeping track of our iteration count, call that z. And second off, changing this, somebody suggested, to a while loop. And I'm going to do a couple other quick edits just to make this a little bit more time-friendly. So here's our final pseudocode. I'm going to set radius equal to 4. What I really mean is 2. I'm just ignoring the square root. So it's actually r squared. Okay? We'll set our max iterations. We still don't want it to run forever, because all those points that spiral in, a regular while loop that checks if we've walked out of the circle, how long would that run for? If the point never leaves the circle, how long would a while loop run for that's checking if the point left the circle? Forever. So we don't want that, so we actually need a second condition. R less than R, and stop less than our total number of iterations. Once per pixel, we need to set z back to 0 and set our new back to the initial point. And then we just track z as we run this loop, and eventually we'll get done and we'll have this thing called color z that we can start messing with. So I'm going to copy this over to Python and write it for you. Woo! Bear with me for just a minute while I switch screens. That appears to be working. Okay. So let's get this and this. And remind me in the back what font size we used. 22. Ah. I can't hit OK. What is happening? Oh, this is real cute, huh? 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 Ah! How's that? Back row. We good? Okay, so welcome back to idle. Once again, all I've done is copy our pseudocode, which we're now just going to go line by line through and translate into Python. So first thing I'm going to do is I like to leave the pseudocode at the top. So I'm just going to copy and paste the whole darn thing and start working my way through it. So the first thing we did was we had some controls. We wanted to set a circle radius equal to 4. How do I define a variable and make it equal to 4? I'm sorry? All right, something like r equals 4. Is that what you said? All right, and if I want to make the max iterations n equal to 100, how do I make that happen? Thank you, other person. Now for the hard part. Huh? Oh, look at that. Caught on tape. 100. I need to make an array the size of the image. If I'm going to do that, what am I missing? Huh? Somebody muttered it. I heard you. Huh? Who said it? What? Yeah, I need the size of the image. So I'm going to define the size of the image up here as a control input. Define image size. And the way I'm going to do it is I'm going to tell it how many x points I want. And for now, let's make a very small image. And the number of points in the y direction I want. And so that's an 11 by 11 grid. How many total pixels is that? I'll let you multiply 11 by 11 on your own. Huh? They murmured it? Okay. What else do I need, though? The number of points isn't enough, is it? If I zoom in, what happens to my window? Do those 11 points represent the same pixels or different pixels? No, that was a stretch. Ooh, man. This is a lot for a Monday morning, isn't it? Okay, so I've got a picture. It starts at some window that shows the whole fractal, and I want to zoom in. What's happened to the axes in my picture? Huh? They've shifted. Okay, so we probably need to define our window limits, such as our minimum x value, which I think I said was -2. Our maximum x value, how about a 1? And then y ran from -1 to 1. And what that lets me do now is define my grid. This is the part you were asking about how do we map values to the pixels. Well, the first thing we needed to do is just fill our z array with a bunch of zeros. Any idea how to do that? I'll show you a little bit of fun code here. I can create an array in Python using a single line of code. and fill it with zeros. Anytime I find myself trying to figure out how to pull that off, I come over here and I play for a minute. Actually, the first thing I do is I go to Google. And on Google, I found a thing that looked like this. Anybody seen anything like that before? That doesn't work here? Okay, so let's unpack this. I'm gonna run it. What do you think is going to happen? Take a guess. Yeah. How many zeros? 11 or 12, something in that order? Yeah, sure. Looks like it's 11. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay? All right, now I'm going to dissect this for you. What does range 11 do? I'm sorry? Yeah, sure, but outside of this code whatsoever, if I type the word range 11 and hit enter, what does that command in Python actually do? Yeah. It makes an array. What's in that array? 0, 1, 2, 3, 4. Oh, it won't print it? Any ideas? Huh? Wonder if I assign it to something, if that'll do it. Doggone object-oriented folks. If you could look inside there, it would look like this. Huh? To print it? Peanut Gallery says I'd have to use a for loop to print that for you. Well, we're going to grab an I value from that. Oh, wait. We could find this out because it's the next thing I wanted to pluck out of my code up there anyway. Will that work? I broke Python. Options. Hello. Shell. Interrupt execution. Thanks, guys. I don't know why Darwin's printed up there, but at the moment I'm starting to feel like he's in charge of this. Huh? What you're experiencing right now is why I usually work over here. So, let's do that. I just made a new file real quick. Let's try this again. What's wrong with my syntax? Huh? Fix my code. Who says this is going to work? Got a couple nods. Huh? Need brackets around what? The I? Ooh, cool, interesting. I got some suggestions to add brackets, probably from somebody who's still thinking about JavaScript. Python's weird in that way because Python doesn't want brackets almost anywhere. All it cares about are these tabbed things. Oh, the square brackets. So, what do they normally do? Something like this? No? That's why Python's so weird. So, let's go back to trying to figure out how the heck this thing works. Shuffle, 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 shuffle. That last 2 minutes, man. Don't say anything important then. Well, I was trying really quick to just unpack this on a typical for loop. Where's that? There, come back here. There we go. I want to make this. Using standard Python syntax, which would be for I in range 11, 0. The fun thing about Python is if you want to run a single command in a for loop, you can write it in this form. And it'll work. Finally got where I wanted to go. So for example, we could do the one that we just did, and it prints out zeros in this array. Why did it end up in an array? Yeah, because I put brackets around it. What do you think is going to happen if I do that instead? Answer my question and I'll let you leave. If you're silent right now, you're holding up the whole class. Yeah. What's it going to print? Zeros? What happens to I every time we go through this loop? Yeah. So we got one that says zeros, one that says count up. Let's find out who's right. Whoa. When I have a 0 here, it's just going to, the command is 0 in brackets. Here, the command is I in brackets. And so we go from I equals 0 to I equals 10. We will continue this on Wednesday. Have a good one. Oh, I know. Yeah. Just trying to do it without breaking in extra libraries. I think I'm going to get forced into it by the time I do visualizations, though. Huh?
Like just like it is in MATLAB.